Hello class 8 students. Today we'll cover some of the topics from the first and the second chapter, especially those which in the posted video from YouTube could not cover it properly because it was not customized. So we'll start with the discussion on the atom. You know that all forms of matter, whether it's solid, liquid or a gas, they are made up of very tiny particles called atoms. Atoms makes a solid, so all the solids are made up of atoms, and even a liquid also consists of those small particles. Liquids are also made up of atoms, and gases also, they have atoms in them. So every form of matter is made up of atoms. Now you know that it was John Dalton, a British mathematician, who was the first one to propose this idea to the Western world that the matter consists of tiny or matter is made up of very small particles called atoms. So today we'll discuss whatever John Dalton conceived, the constitution of matter, how atoms makes all solids, liquids and gases, and different properties of atoms. So according to John Dalton, which is the first theory of atom proposed to the Western world, which we know as Dalton's atomic theory. According to this theory, all forms of matter are made up of very tiny, so tiny that we can't see them with our eyes, we can't see them with microscope also, very tiny particles called atoms. But besides this, he also said another important fact about atoms, that atoms are indivisible. What's the meaning of atoms being indivisible? Indivisible means you can't break an atom, cannot be broken down. Which means you cannot have anything smaller than atom. According to Dalton, atoms are not made up of any smaller particle. They are the smallest. So because they are the smallest, you can't break them to make them further small. So this is what was said in Dalton's atomic theory. But later on, so many different observations and experiments proved that this part, that atoms cannot be divided, is proved wrong. This is wrong now. You know that atoms are made up of tiny, further smaller particles or subatomic particles. So later on it was proved that atoms can be divided. Atoms can be divided into further smaller particles, and you already know the names of those subatomic particles which are present in an atom. They are known as electrons, protons and neutrons. So those smaller particles which constitute an atom, which makes an atom, are called subatomic particles. So today we'll discuss different subatomic particles that makes an atom. So different subatomic particles. You know there are three subatomic particles. They are known as electrons, protons and neutrons. you know, some of these subatomic particles have charge in them. For example, electrons are negatively charged particles. Whereas protons are positively charged. There's one subatomic particle which has got no charge, neither positive or nor negative. It's neutral. So that's neutron. Neutrons are neutral. And if you compare the masses, even though they are small, but they have some small amount of mass in them, electrons are the lightest one. They are very, very light. And these two have almost equal mass. That means if you compare the masses of protons and neutrons, their masses are almost same, whereas electrons are extremely light. So inside an atom, you'll find these subatomic particles: electrons, protons, and neutrons. Now, how do they stay inside an atom? That means, what is the structure of an atom? Where inside an atom you will find electrons? Where do you find protons? Where do you find neutrons? So that structure of atom also we must discuss today. So the next topic is structure of atom. You know, inside an atom, if this is atom, atoms are not this big, they're extremely small, but if you magnify somehow, then you'll find that in an atom like this, at the center, in a small, very small space, all the protons are kept. That means these massive particles of an atom lies in a tiny space at the center. All the protons are here at the center, they are tightly packed, and even neutrons lies at the center. So all the neutrons and protons, they are at the center of the atom in a tiny space packed together, and that part of the atom is called nucleus. Outside this nucleus, electrons go round and round. That means they revolve in a circular path. Like planets go around the sun, electrons also move around the nucleus in several orbits. There are orbits like first orbit or second orbit and third orbit and fourth orbit. In first orbit, you can have maximum 2 electrons. You can have 8 electrons in third orbit, and you can have 18 electrons in third orbit and 32 electrons in fourth orbit. Okay, so this is how an atom is. That inside an atom, all the neutrons and protons are tightly packed at the center. That part is called nucleus. Nucleus must be positively charged. You know why? Because protons are there inside the nucleus, and protons are positively charged, then that makes the nucleus also positively charged. And around this, you've got these electrons revolving. So this is the structure of an atom. Okay, inside this atom, whatever number of protons are present. Okay, one more thing about the atom, that an atom is a neutral entity. Even though atoms are made up of positively charged particles like protons, or they also have negative particles like electrons, but yet as a whole, an atom is neutral. So what makes them neutral in spite of presence of positive and negative? You see, inside an atom, you will have equal number of protons and electrons. Suppose if an atom has 8 protons in the nucleus, then around this nucleus you will have altogether 8 electrons also. So the total positive charge of 8 proton is balanced by the negative charge of 8 electron. That makes as a whole an atom neutral, because positive and negative particles, that is number of proton and number of electrons, are equal. So positive is equal to negative, and that makes it neutral. They cancel each other's charge. So that makes it neutral. Now, there are certain terms used in relation to atom. The terms are atomic number. So you could be asked, what is atomic number? of an atom. Atomic number is nothing but the number of protons that lies inside the nucleus. Suppose a nucleus of an atom has, let's say, 8 protons. So what is the atomic number? 8, because it has got 8 protons, because atomic number simply means number of protons. And in a neutral atom, if you have 8 protons, you will also have 8 electrons. So that way atomic number also can represent the number of electrons. Okay. Then there is something called mass number. Mass number is the total number of neutrons and protons. For example, if you have any atom inside the nucleus of which, if you have 8 protons and let's say 8 neutrons, the total 8 plus 8, that is number of proton plus number of neutron, makes it 16. So atomic mass number will be 16. Okay. So this is how you can define atomic number and mass number. Okay, so I'll give you some examples. I want you to copy this part, at least this atomic number and mass number, as number of protons and total number of neutrons and protons. Okay. Now next thing is, I'll be giving you some atom, let's say carbon atom. There's one particular type of carbon atom. Its atomic number is 6, and let's say its mass number is 8. Can you find some meaning out of this value of its atomic number and mass number? That means, can you find out how many protons are there in this atom of carbon? You know, proton is nothing but the atomic number. Atomic number is the total number of proton that lies inside the nucleus. So since atomic number of carbon is 6, so there are 6 protons. And if this carbon atom is neutral, you know, in a neutral atom, number of proton always equals to number of electrons. So electrons will be also 6. What is mass number? Mass number is the total of neutrons plus proton. So total of neutron and proton is 8. So if you subtract, and this atomic number is nothing but protons, you know. So from mass number, which is the sum of neutrons and protons, if you subtract the number of protons, that is atomic number. So mass number is n plus p, neutron plus proton. And if you subtract atomic number, that is proton, proton cancel. So what you get is number of neutrons. So to calculate the number of neutrons in an atom, what do? You simply subtract atomic number from mass number, because mass number is a total of neutrons and protons. From there, if you subtract atomic number, which is the number of protons, then proton will be subtracted. So you will get number of neutrons. So here, how many neutrons are there? To calculate, what you're supposed to do? Mass number minus atomic number. So neutrons will be, sorry, this mass number is not 8, its mass number is 14, okay? That's what. This mass number is 14. So what is the number of neutrons? 14 minus 6, that's going to be 8. Yeah. So this is how you can use atomic numbers and mass numbers. Today we'll practice balancing some of the simple chemical equations. So the first one we have here is a reaction between calcium oxide, which is also known as quicklime, with water. And it leads to the formation of calcium hydroxide, which is also known as slaked lime. So in this equation, you've got two reactants here, and there's a product. So how do you balance any chemical equation? It is simply done by counting atoms. You've got to add or count atoms towards left hand side, towards the side of the reactants, and then count the atoms towards the right hand side, that is the side of the products. For example, here you've got one calcium atom. The other side also you've got one calcium atom. So calcium is already balanced. There's a lot of fan noise. Okay. Then, so calcium is balanced. Let's say hydrogen. Hydrogen is also, how many you've got here? 2. And the other side you've got 2 hydrogen. Even hydrogen is balanced. Lastly, oxygen. You've got 2 oxygen on left hand side and 2 oxygen on right hand side. So amazingly, this equation is balanced by itself. So some of the equations are like that they need no balancing. So this is one such equation. So this is already balanced. The second one is the reaction where hydrogen gas burns in presence of oxygen to form water. So this is a molecule of hydrogen you've got, and oxygen molecule is combining to form water. So how do you balance this? You see, you've got 2 atoms of hydrogen here and 2 atoms of hydrogen on right hand side. Hydrogen atoms are balanced already. Whereas oxygen atom, you've got only 2 here. You've got 2 and the other side only 1. So how do you balance? You see, when you balance, you are not allowed to write anything towards right hand side. You know, like you can't change anything here. Whatever you have to write in front. So 2 atoms of oxygen here. So you've got to place 2 as a coefficient here to balance that. So 2 atoms of oxygen. But that has disturbed the number of atoms of hydrogen. Now you have 2 into 2, 4 atoms of hydrogen. Whereas you've got only 2 this side. So you can place 2 here, which makes number of hydrogen atom 4 again on left hand side. So that way you've got 4 hydrogen atom and 2 oxygen atom. It's balanced. Okay. So we'll try the third one, where nitrogen gas is burning with hydrogen gas. It's some kind of combustion, you can say, or hydrogen is burning nitrogen, forming ammonia. That compound is called ammonia. It's a gas. So how many nitrogen you've got on left hand side? 2. Whereas on right hand side only 1. So you can write 2 here. You should not change anything here. You can't put it as a subscript. That's not allowed. So whatever comes while balancing has to come in front as coefficient. Okay. So because we had 2 nitrogen this side, so in order to make 2 nitrogen on the other side, we place 2 there. That balances nitrogen. But you've got only 2 hydrogen on left, whereas 3 into 2, 6. 6 hydrogen atoms are on right hand side. So 6 here, only 2 there. So how do you balance? What coefficient, if you write here, will make hydrogen 6? It is 3, because 3 2s are 6. So that way you balanced hydrogen also. 6 hydrogen and 6 hydrogen and 2 nitrogen, 2 nitrogen. So the equation is balanced. Okay, so I've got one more reaction where this compound, you see this compound has got carbon and hydrogen atoms in it. Compounds with only carbon and hydrogen, they are known as hydrocarbon. So this is one such hydrocarbon, and it's burning in oxygen. So when hydrocarbons burn in oxygen, carbon and oxygen forms carbon dioxide. You must be knowing the formula of carbon dioxide is CO2. And hydrogen and oxygen forms water. So that's the equation you've got. Now how do you balance this? You've got 2 carbon on left, whereas only 1 carbon on right. So place 2 here as a coefficient, that makes carbon 2. Then you've got 2 hydrogen here, and there also 2 hydrogen. Hydrogen is balanced. Lastly, we've got oxygen. 2 oxygen on left hand side, 2 into 2, 4 oxygen on right hand side. Here you've got 4, remember, but you've got more oxygen on the other side. 2 and 2, 4, and there's 1. 2 into 2, 4 oxygen, plus 1 more oxygen. total is 5. There are 5 oxygen atoms on right hand side, whereas you've got 2 here. So how do you make it 5? If you write 5 here, the problem is that 5 into 2 will make it 10, whereas you've got 4 plus 1, 5 only on the other side. So you can write 5 by 2. You know, if you write 5 by 2, what happens is this 2 and 2 cancel, so total number of oxygen on left hand side becomes 5. This 2 and 2 cancels. So you've got 5 here and 4 plus 1, 5. It's balanced. But the problem is we don't write fractional coefficients most of the time. This is a fraction. So you can turn this fractional coefficient into a whole number by removing this 2. How do you remove this 2? If you multiply this equation, both sides, left hand side and right hand side, by 2, then you can get rid of this 2, because when you multiply this with 2, 2 and 2 cancels. So what you're supposed to do is multiply both sides by 2, because you can't multiply only left hand side by 2. Whatever you do on left, you've got to do it on the right. So we are multiplying both sides by 2 just to remove this denominator here, just to remove this fraction. So 2 into 1, 2. If I multiply 2 here with 2 here, that 2 and this 2 at the denominator cancels, so it leaves only 5. And 2 into 2 this side will become 4, and 2 into 1 will be 2. So now this equation is balanced. Let me count how. 2 into 2, how many carbon? 4 carbon. Hydrogen, 2 into 2, 4 hydrogen. 2 into 2, 4 hydrogen. 5 into 2, 10 oxygen. 4 into 2, 8 plus 2 oxygen, and that amounts to 10. So that way this equation is now balanced. We'll try another one. You see, this second one is similar type. This compound here, instead of burning, it's breaking down to form carbon and hydrogen. This compound is breaking to form carbon and hydrogen. So how do you balance it? You've got 2 carbon here, only 1, so write 2 here. 2 hydrogen this side, 2 hydrogen. It's already balanced now. So the equation is balanced. Next one. Okay, next one shows how hydrogen and chlorine are reacting to form a gas called hydrogen chloride. So how do you balance this? 2 hydrogen here, only 1, so you can write 2 in front. 2 chlorine, 2 into 2 chlorine, it's balanced. So this equation is also balanced. See, there are more such equations, so we'll try to balance them also. Okay. You must be knowing this particular equation from our last video which I had posted, that in the preparation of oxygen in lab, we start with this compound called potassium chlorate. This radical ClO3 is known as chlorate radical. So this compound is known as potassium chlorate, and this, when heated, will break down to form potassium chloride and oxygen molecule. So this is the equation for the reaction involved in the preparation of oxygen gas, which you had seen in the previous video from YouTube I had posted. So how do you balance this one? Count how many potassium atoms you've got on left. 1. Potassium is balanced. Chlorine 1, chlorine 1. Chlorine is also balanced. Oxygen 3, and that side 2. So how do you balance 3 and 2? You see, the LCM of 3 and 2 is 6. So if you try to make both sides 6 oxygen atom, it will be balanced. So how do you make this 3, 6? By multiplying with 2. 2 into 3, makes 6. And how do you make this 2 6? By multiplying with 3, because 3 into 2 makes 6. So oxygen is balanced, but that way I have disturbed the potassium atom and chlorine atom by placing 2 here. So now we have 2 potassium this side, so I've got to make potassium 2 again on right hand side, and chlorine 2 this side, chlorine 2 that side. So now the equation is balanced. You've got to pause these videos to copy all this, or you can practice yourself also instead of directly copying it from the board. And there's this 8th one, where this compound called calcium carbonate, you must be knowing calcium carbonate is chalk, so it's reacting with hydrochloric acid, HCl, and it's breaking down to form calcium chloride, carbon dioxide, and water. So how do you balance this? 1 calcium, 1 calcium on right hand side, 1 carbon, 1 carbon, 3 oxygen, you see, and how many you've got? 2 plus 1, 3. Hydrogen, 1 on left, but there are 2 atoms on right. So how do you make this 2? By placing 2 here. So 2 hydrogen balanced. Now 2 chlorine and 2 chlorine, that is also balanced. So this one's long equation, but yet the balancing is very simple. You just have to place 2 as a coefficient of HCl. That's it. The equation is balanced. Now next, after balancing the equation, next we'll learn about the catalyst, because from the previous video of preparation of oxygen in lab, you must have noticed that potassium chlorate, this compound, when heated in a test tube, will break to form potassium chloride and oxygen gas. You have already balanced this equation also. But this reaction is not that simple, because if you try to break potassium chlorate to prepare oxygen like this, a lot of heating is required. About 650 degrees Celsius is required. Reaching to this temperature only, potassium chlorate starts breaking. But then still the breaking process is very, very slow. This reaction is very sluggish and slow. So even after reaching to 650 degrees Celsius, which is quite a high temperature, potassium chlorate won't break rapidly to give you oxygen fast. So this oxygen will evolve very gradually and slowly. So how do you make this process fast? To make this process fast, what we do is we put this compound called manganese dioxide. Its formula is MnO2. Mn is a symbol of this element called manganese. So it's a compound between manganese and oxygen. It's known as manganese dioxide. What do is they take a lot of potassium chlorate and mix a small proportion of manganese dioxide. So what this manganese dioxide does, it itself will not break, it will not take part in the reaction. Nothing will happen to manganese dioxide on heating, but it makes this process of breaking of potassium chlorate easy. It makes it easy by lowering the required temperature from 650 to only 250 degrees Celsius. Now instead of breaking at 650 degrees Celsius, potassium chlorate will break quite easily at 250 degrees Celsius, forming potassium chloride and oxygen. So that way, by the use of manganese dioxide, the reaction becomes easy. But it not just becomes easy, it also becomes fast. Now potassium chlorate starts breaking very rapidly, giving oxygen quickly and instantly. So the use of manganese dioxide has made this reaction fast and has made this reaction easy, because we need not heat up to 650 degrees Celsius. Potassium chlorate starts breaking at 250 degrees Celsius by the use of this substance. So what do you call these types of substances which will not take part in the chemical reaction but makes reaction go fast? Some of these substances in some other cases are also used to make the reaction slow also. In some cases we need to slow down the reaction instead of making it fast. So some substances are capable of not taking part in the reaction yet slowing down the reaction. So these substances, what do? Without taking part in the reaction, they change the speed of the reaction. In some cases they make the reaction fast, or in some cases they make reaction slow. What do you call such substance which changes the speed of the reaction without itself taking part in the reaction? They are known as catalyst. In fact, the catalyst which makes the reaction fast and easy is known as a positive catalyst. And a catalyst which makes the reaction slow and difficult is known as a negative catalyst. So what is the role of manganese dioxide in the preparation of oxygen in lab? You know that oxygen gas is prepared in lab by heating potassium chlorate, but the reaction is very slow and requires a lot of heating. So we use small amount of manganese dioxide here in a ratio of 5:1. We take 5 parts of potassium chlorate, let's say 5 grams. To that we mixed only a small amount, 1 gram of manganese dioxide. And this substance called manganese dioxide won't take part in the reaction, yet it makes the reaction easy and fast, and such a substance is called catalyst. The role of manganese dioxide here is to make the reaction fast and easy, so it acts as a positive catalyst. Okay, so I thought like maybe in that video where preparation of oxygen in lab was shown, I thought like maybe you didn't understand the role of manganese dioxide properly as a catalyst, so I wanted to give this extra information about manganese dioxide here. The next thing we've got is next thing we've got here is something called combustion from the chapter of oxygen. You know that combustion is simply burning. When substances burn, the process is called combustion. You know, substances burn, like for example carbon. Carbon is present in coal, charcoal. Carbon burns in presence of oxygen. In fact, most of the substances burns in presence of oxygen. That's why oxygen is also known as supporter of combustion, because oxygen helps other substance to burn. So carbon burns in oxygen and forms carbon dioxide. Sulfur burns in oxygen and forms sulfur dioxide. These are all gases. And even metals such as magnesium burns in oxygen, forming magnesium oxide. So these reactions are known as combustions. You've seen a lot of substances burning. Everything burns with the help of oxygen, and these reactions are called combustion. Combustion is a rapid process. It's not a slow reaction. And it forms the oxide of these elements. So you've got to read some more combustions from your book. There is a detailed discussion on what is combustion, okay, in your book. And it's also compared with another process here called rusting in your book. So what is rusting? You know that most of the time when you keep iron articles in open air, especially in a moist place, iron gets rusted. So you've seen rusting where iron combines with the oxygen. During rusting, what happens is that iron which is kept in open air has oxygen in it, will combine there to form iron oxide. That's the formula of iron oxide, because the valency here of iron is 3 and oxygen is 2. So when you cross multiply Fe2O3, so you get that compound called iron oxide. And later on, that iron oxide formed will combine with some water molecules present in the moist air and forms this hydrated iron oxide. Hydrated, why we call this hydrated? Because there's some water picked up by iron oxide, and this is the formula of rust. So basically rust is nothing but it's the oxide of iron with some water in it. Okay, so you can consider rusting also as some kind of combustion, because like combustion, like elements combine in combustion with oxygen to form their oxide, even in rusting, iron is getting combined with oxygen to form its own oxide. So it's exactly like combustion. But rusting compared to combustion is a slow process. You know that iron will not rust in minutes. It takes days and sometimes weeks to get rusted. So rusting is a slow process, whereas combustion is a fast process. There are some more differences between combustion and rusting. During rusting, no light is produced. When iron gets rusted, we don't see any glow there, so no light is produced. or even if heat is produced, it is dissipated so gradually that we don't feel any heat being produced. So we can say that almost no perceptible light or heat is produced during rusting. Whereas in combustion, you know that when things burn, light is produced and heat is also produced. So that's another difference between combustion and rusting. And the similarity you already know, that both in combustion and rusting, it is the oxygen which combines with the elements. When substances burns, it burns with the help of oxygen. Oxygen acts as a supporter of combustion. And when rusting happens, rusting is also supported by oxygen. Iron combines with oxygen to form iron oxide. So this is how one can compare combustion with rusting. The next thing I want you to revise today is the identification of atoms and molecules. You know that most of the time atoms are reactive and they don't stay alone. Reactive atoms will combine with one another, forming a group called molecules. For example, when we write hydrogen gas, we don't write H, because you know that hydrogen, H represents one atom of hydrogen. This is just one atom of hydrogen. This is one atom of oxygen. This is one atom of chlorine. But all these atoms are reactive, so when they are kept in contact to one another, they quickly combine. In case of hydrogen, two atoms join to form an entity called molecule of hydrogen. So when you write H2, it represents one molecule. This is one atom of oxygen, but its atom combines with the other atom of oxygen. Two of them will combine, forming a molecule. So this is a molecule of oxygen. Similarly, chlorine atoms are also reactive, so when they are in contact with other chlorine atoms, they quickly combine. Two of them will combine to form a molecule. So in many cases, two atoms of the elements will combine to form a group called molecule. So when you only write H, that represents one atom of hydrogen. But when you write H2, that is one molecule. This is one molecule of oxygen. This is one molecule of chlorine. So when you write 2H2, what does it represent? It represents two molecules of, because this is molecule of hydrogen. So two molecules of hydrogen. When you write 3 here, 3 molecules of oxygen. When you write 4 here, 4 molecules of chlorine. Okay. So what's the difference between 2H and H2? 2H is 2 atoms of hydrogen, whereas this is one molecule of hydrogen, because the coefficient here is 1. When you don't have anything, you've got to understand there is 1 there. So this is 2 atoms of hydrogen, whereas this is a molecule of hydrogen, one molecule of hydrogen. This is 4 atoms of hydrogen, and this is 4 molecules of hydrogen. How many atoms of hydrogen you've got? If you count all the atoms here, 4 into 2, 8 atoms of hydrogen, or you can also say 4 molecules of hydrogen. Okay, so this difference between atoms and molecules and the ability to count atoms and molecules in the molecular structure is very important. So I want you to practice. With this, I think I have revised everything. So whatever was not present in those videos which I had posted earlier, I think this will complement that. So hope it will complete everything. So I want you to prepare it properly, because tomorrow you've got your exam.